Okay, in today's lecture, we're going to start our Chapter 6 material on vector calculus. So in our first section, 6.1, we're going to define and familiarize ourselves with something called a vector field. We're going to work a lot with vector fields throughout Chapter 6. So in this section, we'll just define them and see what they could be used to represent. So let's start by giving a little background with where vector fields might be useful in different sciences. So here, vector fields are used frequently in the study of fluid dynamics. That's probably one of the biggest applications of vector fields. Also, gravitation, electronics and magnetism, and various other sciences. So let's start by defining what exactly is a vector field. So here's our definition. We would say a vector field in R2, in the plane, is a function, capital F, notice that it is given in boldface, which assigns a two-dimensional vector, which we will denote as capital F of xy, to each point xy in some subset D of the plane. So a vector field in the plane is a function that assigns a two-dimensional vector to every point xy in the plane. So it's exactly like a vector function that we were working with in Chapter 3, but a vector field is a function that takes a point as its input rather than a specific value, like say just one specific number, like r of t is what we were working with in Chapter 3 for our vector functions. Vector fields are like multivariable vector functions. They take points xy or xyz and define vectors. So in a similar way, we could define a vector field in space as a function f that assigns a three-dimensional vector, f of xyz, to every point xyz in some subset of space. And the subset D that we're referring to in this definition is called the domain of that vector field. So typically, the way that we define vector fields, or the way that we express them, is in terms of their component functions. So for a two-dimensional vector field, f of xy, we have a two-dimensional vector whose first component is given by some function p of x and y, and the second component is given by another component function q of x and y. And for a three-dimensional vector field, f of xyz, we have a three-dimensional vector whose components are defined by the component functions p, q, and r. So one way that we can visualize a vector field and think about what it might represent physically is by using a vector field diagram, sometimes called a field diagram or a phase portrait. So the way that we're going to obtain a visualization of a vector field is to draw an arrow, which would be the representation of the vector f of xy, which has its initial point at xy. So we're going to choose a bunch of points in the xy plane, find the vector given by the field at that point xy, and then draw the representation of that vector starting at the given point. So this graph of our vector field gives us some impression of what exactly our field is describing, and sometimes will tell us some useful information about the properties that that field might have. We'll see some of these properties as we move through Chapter 6. So as our first example, we are asked to sketch the vector field f of xy, whose component functions are x and y. So how we're going to do this, I've given a little diagram below here. So this is a graph of XY axes in the plane. And we're going to choose different points in the XY plane and find the vector that is described by this vector field at that point. So in our first example, we have our component functions are x and y. So let's start choosing some points. I'm going to start with the point 0, 0. And my vector field f, if I evaluate at the point 0, 0, gives me the vector 0, 0. You plug your x and y values into these component functions to find the corresponding vector. So we have the 0 vector, which has no magnitude or direction. So at the origin, we have the 0 vector. There is no vector representation. We might just draw it as a single point. So let's start choosing some other points. For instance, f of 1, 0 is the vector 1, 0, since the component functions are just x and y. So in our xy plane here, from the point 1, 0, we're going to draw the representation of the vector 1, 0. So that would be the vector of length 1 moving along the positive x-axis. So its y component is 0, so it's only moving horizontally 1 unit here. Similarly, we could choose some other points. Let's take maybe f of negative 1, 0, which would be the vector negative 1, 0. So from the point negative 1, 0, we draw the representation of this vector, negative 1, 0. So that would be the vector moving 1 unit to the left, and it does not move in the vertical direction. So let's choose some other ones. We could take the point 0, 1, which would be the vector 0, 1. So in the xy plane, from the point 0, 1, we draw the representation of this vector 0, 1. So that would be the vector moving 1 unit in the positive y direction. And f of 0, negative 1 would be the vector 0, negative 1. So from the point 0, negative 1, we draw the representation of this vector. Its x component is 0, y component is negative 1, so moving down 1 unit in the y direction. And then we can start choosing other points from here. So for instance, if we chose the point 1, 1, we have the vector 1, 1. So from the point 1, 1, we draw the representation of this vector. Its components are 1, 1, so we're moving from this point 1 unit to the right and 1 unit upward. So we have the following vector. And we see if we start choosing other points, for instance, negative 1, positive 1, well, the vector representation, negative 1, positive 1, would look like this. Choosing positive 1, negative 1, we would have a vector positive 1, negative 1. Choosing the point negative 1, negative 1, we get the vector negative 1, negative 1, and so on. And we see that the further that we move outward from the origin, that is, the larger that I choose the values of x or y, my vectors are of larger magnitude. So if we start choosing other points here, we're finding larger magnitude vectors. So by choosing these different points in the plane and drawing the vector representations that start at those points, we start to get an idea of what our vector field looks like, or what this might describe. So if our vector field, f of xy in this example, maybe represents a force, we see that it's sort of a repellent force that is moving outward from the origin, And the further that I get from the origin, the larger the magnitude of this force. So in this first example, we have an example of what is called a radial field. Now, a radial field is a vector field where every vector points either directly towards or directly away from the origin. So any vector field where all of our vectors are pointing towards some central point, like the origin, or directly away from some central point, is called a radial field. Now, in this example, our vector field had component functions x, y. So we see that sketching our vector field here was not very difficult to do by hand. For some more complicated vector fields, we might need software to assist us, and I'll show you how to do that in just a moment. But let's look at one other example of doing this by hand first. So in our second example, we're asked to sketch the vector field f of xy, whose component functions are negative y and x. So again, if we start at the origin, 0, 0, then we get the 0 vector. So here, let's write it out. F of 0, 0 is the vector where both components are 0, so it has no direction, no magnitude. Now, if we start choosing other points, let's say that we choose the point 1, 0. Well, here, if y is 0, then our first component is 0, and if x is 1, then our second component is 1. So from the point 1, 0 in the plane, we're going to draw the representation of this vector, 0, 1. So that is the vector which moves upward 1 unit. Now, if we choose some other points, let's say that we choose negative 1, 0, we would have the vector 0, negative 1. So from the point negative 1, 0, we get the vector moving downward 1 unit. So let's choose some other points. If we choose the point 0, 1, well, if if y is 1, our first component is negative 1, and if x is 0, our second component would be 0. So from the point 0, 1 in the xy plane, we have a vector moving 1 unit to the left. Let's do some other ones. Here, f of 0, negative 1 would have a component of positive 1 and 0. So from this point, we have a vector moving 1 unit to the right. Let's look at some other ones maybe. Here, if we take f of 1, 1, we have the vector negative 1, positive 1. So from this point 1, 1 in the xy plane, we have a vector which is moving 1 unit left and 1 unit upward. If we choose other points, we get similar results here. So if we choose a few others, we can see what's happening here. Now, of course, to draw many of these arrows, we see it can start to be a little bit tedious to do this by hand, or we may not always have the easiest functions to work with. Say if f of xy has a component function involving maybe exponentials or logarithms, something that's not easy to calculate the exact value of by hand, then doing these vector field sketches by hand becomes very tedious or impossible. So we can use software to sketch these direction fields. Now there's some free software that's available online for sketching vector fields. So let me show you how to use that for this vector field before we look at our next examples. So let me switch over to my browser. So here, my recommended free online version of a vector field plotter is through Desmos. So here I show you if you Google search Desmos vector field, this first result that pops up is called a vector field generator. So you can click on that link, and it will bring you to this field generator. So it looks very complicated on this left-hand side, but using this is actually very simple. The only things that you need to do in order to use this are modify these first two rows on this left-hand side, what we've got labeled here as F1 or F2. So F1 is going to be the first component function for your vector field. In that last example, we had negative y. So here, you can click in this box to modify F1. Here we had, down at the bottom, a little text box pop up. So we had negative y for our first component. And our second component function was positive x. And this graph will automatically adjust here based off what you changed your component functions to. So if we zoom in on this a little bit, we see these little arrows representing the different vectors in the xy plane describing this field. So in our plot that we've generated here, we can see, of course, that this field appears to describe some sort of rotation about the origin, like a counterclockwise rotation. So going back to our example, this is an example of something called a rotational field, where every vector f of xy lies tangent to a circle of radius square root x plus square root of x squared plus y squared. So this is an example of what's called a rotational field. So if it's a velocity field, this might be used to describe, say, like wind velocity in a hurricane. If we're talking about like the velocity of fluid, this might describe like a whirlpool, which is rotating counterclockwise about some center point. So this software can help us get very high quality direction fields without having to do this by hand. So as some other examples of this, in our next one, we are asked to sketch the vector field f of xy, which is negative 2y, negative 2x as its components. And then we're asked the question, is this vector field radial, rotational, or neither? So now that we have the use of Desmos to sketch our field, we don't need to do this by hand. So here, let's use Desmos to generate the graph of our field. So here, the first component in this example was negative 2y, and our second component was negative 2x. So here, our field updates accordingly. Let me zoom out a little bit. So we get a vector field that looks something like this. And so we can see that this field is neither radial nor rotational. It's certainly not rotational. We can see that's pretty obvious from the look of our field. And it is not radial. Some of our vectors are pointing towards the origin, some directly away from the origin, but there's these other vectors which are not pointing directly towards nor away from the origin, so it is also not radial. So we get a sketch of our field here, and to address our question that was posed in this example, the field is neither rotational nor radial. So in the next part of the notes here, I had mentioned that software can be used to generate these high quality graphs of more complicated vector fields in 2 or in even 3 dimensions. Certainly in space, we wouldn't want to do this by hand. So I give a few examples which you can double check in Desmos that these vector fields have this appearance. But I say use software to plot the given vector field. So this first one had component functions y and sine of x. It gives us a vector field that looks something like this. So these plots I generated using Maple. Now, Maple's not free, so you likely don't have this at home to use, but you can use that Desmos plotter, which is free online, to generate graphs similar to this. So in this first one, let's go ahead and graph it. Our first component for that vector field was y, and then our second component function was sine of x. So here, if you have like trig functions or different functions that are needed for your component functions, you can see in our keyboard here in the top right, there's a button that says functions. So if we click functions, we can choose which one we're dealing with. If it's a trig function, if we're working with logs, we can go to this miscellaneous section. We've got the natural log, log base 10, exponentials, and so on. So here for our trig function, we had sine of x, and we can see here that our vector field updates, and we get, it's not quite as nice as the picture that we generated using Maple, but we see the same sort of behavior for the vector field here through Desmos. So in these other ones, I'll let you play around with Desmos on your own to plot this next example, where our component functions were the natural log of 1 plus y squared and the natural log of 1 plus x squared. Here you get a vector field that looks something like this. Or in 3 dimensions, you can use software to generate a plot of a vector field. So this first one, as an example in 3 dimensions, we have f of x, y, z, where the component functions are 2x, 2y, and 2z. So if we choose several points in space, x, y, z, we see that the larger that x, y, z become, the larger the magnitude of this vector. And it appears from our plot here that each of these vectors is moving outward from the origin. When x is equal to 0, y equals 0, and z equals 0, we have our origin. And all these vectors appear to be moving outward from the origin and increasing in magnitude the farther that we get from the origin. So this is an example of a radial field in 3 dimensions. Now there is a tool in Desmos, if you Google search Desmos 3-dimensional vector field plotter. There's a similar program to what I showed you for the plane plotter, but it's not very good, to be honest. It doesn't give very high quality pictures, that free one. Again, this one that I've shown here in the notes was plotted using Maple, which is a better software, but unfortunately it's not free. But you can use that Desmos 3D plotter to get some idea of what a vector field would be describing in space instead of the plane. So in the last part of this section, we can define a specific type of vector field that's associated with multivariable functions, which we've already been working with, namely the gradient of a multivariable function defines a vector field. So we sometimes call this a gradient vector field. So let's define it. Let's say that we have a function f of 2 variables, x and y. We would define the gradient vector field of that function as the vector field denoted by gradient of f, or grad f, and the component functions of this vector field are the partial derivatives of our function f with respect to x and y. So we get a vector field in 2 dimensions for a 2-dimensional function. Or if we have a function of 3 variables, f of x, y, and z, then we would define its gradient vector field as grad f of xyz, which is the three-dimensional vector field whose component functions are the partial derivatives of f with respect to x, y, and z. So gradient vector fields will have some nice properties that we'll explore throughout Chapter 6. But let's look at some examples, just reviewing the gradient in our new context of thinking about it as a vector field. So in this first example, we are told to find the gradient vector field for the function f of xy is equal to the square root of x squared plus y squared. So here to find grad f, which is a function of x and y, we would take the two-dimensional vector whose first component would be the partial derivative of our function with respect to x. So here, making use of the chain rule, the derivative of our outer function, the derivative of square root of a function is given by 1 over twice the square root of that same function, or 1/2 of that function raised to the negative 1/2 power. And then we multiply by the derivative of the inner function with respect to x. So here, derivative of x squared would give us 2x, and then y we're treating as a constant. Now, to get the second component, we take the partial derivative with respect to y. So the derivative of the outer function is again 1 over twice the square root of x squared plus y squared times the derivative of the inner function with respect to y gives us 2y. So if we simplify a little bit, we have our gradient vector field, that is grad f, which is a function of xy, is the two-dimensional vector field where our first component, we can cancel the factor of 2 on top and bottom. We're left with x divided by the square root of x squared plus y squared. And our second component, similarly, if we cancel the factor of 2, we're left with y over the square root of x squared plus y squared. So this would be our gradient field for that function. And this is an example of something called a unit vector field. If we think about taking the magnitude of this gradient vector, we would be taking the square root of the sum of the squares of the components. So we would have, for our first component, x squared over x squared plus y squared, plus, squaring our second component, we have y squared over x squared plus y squared. So here, under the radical, summing these terms, we're left with x squared plus y squared over x squared plus y squared. So that's the square root of 1, or 1. So we see no matter what the value of x and y are, that is for any point that we take in the plane, the vector that we would have at that point is a unit vector. It has magnitude 1. So these types of vector fields that always describe unit vectors are called unit vector fields. So this is an example of one that is a unit vector field. So let's look at another one. In this next example, we are asked to find the gradient field for the three-dimensional function f of x, y, z is x times natural log of y minus z. So here, our gradient field, since f is a function of 3 variables, will be a three-dimensional vector field. Our first component will be the partial derivative of our function with respect to x, which is going to be 1 times the natural log of y minus z. Our second component would be the derivative with respect to y. So here we have the constant x, and using the chain rule, the derivative of natural log of a function is 1 over that function, times the derivative of the inside with respect to y would be 1. And then for our last component, we have our constant x times the derivative of the natural log of y minus z using the chain rule. Well, the derivative of the outside is 1 over y minus z times the derivative of the inside with respect to z, which would be negative 1. So that just makes our 1 in the numerator a negative 1. Or if we clean this up a little bit, we have our gradient field of f is the vector field whose first component is given by the natural log of y minus z. Second component is x over y minus z. And our third component is negative x over y minus z. So this would be the gradient field for that function. So here, if we're asking for the gradient vector field of a function, we're just asking you to find the gradient of that function. And it describes some vector field, which we could visualize by using Desmos or sketching our graph by hand. To finish up with this section, we will define something known as a conservative vector field. These conservative vector fields have very nice properties, which we'll explore more throughout chapter 6, but in this first section we will define it. So any vector field f is called a conservative field if it can be considered as the gradient of some scalar function. So we would say a vector field is called a conservative vector field if there exists some function f such that our vector field would be described by the gradient of that function. And in this case, the function f, which would have our vector field as its gradient, is called a potential function, or sometimes called a scalar potential for that vector field. We will describe throughout chapter 6 some of the nice properties that these conservative vector fields have, and we'll introduce techniques for determining whether a given vector field is conservative or not.